In the first video in this series, we learned about what it means for a digit to be significant and how to represent those digits. In the second, we learned about how to use significant figures in math. In this video, we will expand upon using significant figures and scientific notation in math with more complex examples. Exams with significant figures will often contain questions that require using more than one rule at once, and in different orders. We will work through examples using scientific notation, addition, and multiplication rules. Let's start with a relatively simple example using scientific notation in multiplication. How would we determine the answer to this problem? Well, first we should plug in the coefficients, this number and this number, into our calculator, which 6.63 times 3.0 equals 19.89. Then we can figure out what the base becomes, which we can do by adding the powers of each one. So 10 to the negative third times 10 to the fifth we can do by adding negative 3 and 5 to get 10 squared. However, if we just put those together and write it as 19.89 times 10 squared, we'll have two things wrong. The first problem is that this new coefficient is not below 10, which means that we can still divide by 10 to make the coefficient smaller. The second problem is that 19.89 has 4 significant figures, while 3.0 only has 2. So we need to round 19.89 to only have 2 significant figures. So, solving the first problem, we can divide our coefficient by 10. So, divide by 10, and that will give us 1.989 times 10 to the third. Now we need to add 1 to the power here to make sure that the number is still the same. We've divided the coefficient by 10, but to keep the number the same, multiplied the base by 10. So this gives us 1.989 times 10 to the third. Then we can solve the second problem by rounding until we only have 2 significant figures. We will keep our 1.9 because that's 2 significant figures, and then look at the 0.089 to figure out what to round it to. And that's above 5, so this will become 2.0 times 10 to the third. Next, let's combine our rules for addition with our rules for multiplication. Take, for example, the problem 155 minus 113 in parentheses times 12.5. Now at first glance, it looks like the answer to this problem should have 3 significant figures because 155, 113, and 12.5 all have 3 significant figures. But when you subtract 155 by 113, you get 42, which only has 2 significant figures. And you do that first because it's in the parentheses. So the initial math gives you 42 times 12.5 equals 525. But because 42 only has 2 significant figures, we need to round it to only have 2 significant figures. So the answer should be 530. Or, if we want to be less ambiguous about the number of significant figures, 55.3 times 10 squared. Finally, let's use an example combining all of our rules. So 1.2 times 10 squared for our scientific notation term, plus 5.6, all inside parentheses, divided by 32. So step one, as always, is to start inside the parentheses. Now this looks tricky because 1.2 times 10 squared is in scientific notation, but we can make this easier by just writing 1.2 times 10 squared is equal to 120, and use that in our operation instead. So 120 plus 5.6 equals 125.6. Now you might expect that from our addition rules we would ignore this 0.6, but we can't actually do that because we can't round our number until the very end of the problem. So that means that this 0.6 is not significant. So we should just continue using it as 125.6, but we have to be aware that the 0.6 is not actually a significant figure. So carrying that to our next operation, do 125.6 divided by 32. We can plug that into our calculator and get 3.925. But of course, 32 only has two significant figures, and while we ignore this 0.6 here, the remaining number still only has three significant figures, and so we still reduce 3.925 to two significant figures. So our final answer is 3.9. As you can see, the answers to some of these problems may not look super intuitive at first because you have to leave out some numbers that you would expect you would need. But our precision tells us that these are the only numbers that we really know. And those are the only numbers that are really useful in real-world use, as the next few videos will show.